Welcome to our deep dive into the world of magnetism.
It's going to be a fascinating one.
Yeah, it is. Get ready to be amazed.
That's right.
We're going to help you prep for your Physics 220 exam
Yes.
by exploring all those class notes you've been taking on magnetism.
Absolutely.
And, it's not just textbook stuff.
No.
We're talking real-world applications.
Real world.
That might just blow your mind.
Yeah.
Did you know how an MRI machine works?
Or what makes an electric guitar sing.
Or a motor spin?
We're about to find out.
Yeah. The applications of magnetism are all around us.
They are.
Let's start with a bit of history.
Okay.
Did you know that humans have been fascinated by magnets for centuries?
Really?
Long before electricity was even a thing, people were already using naturally occurring magnets called lodestones for navigation.
Lodestones.
Yeah.
That's fascinating. So how did a simple rock become like an essential tool for exploration?
Well, lodestones are actually a type of iron oxide called magnetite.
And they have a unique property. They're naturally magnetic. What's incredible is that the Earth itself acts as a giant magnet with its own magnetic field.
Right.
Lodestones, being magnetic, align themselves with this field and boom, you have a compass.
That's amazing. It really puts into perspective how long humans have been, intrigued by magnetism.
Yeah.
Our notes mention that things really took off in the 19th century.
Yeah.
With a pivotal discovery in 1819, something about a guy named Ørsted.
Ah, yes. Hans Christian Ørsted, his discovery changed everything.
Wow.
He was experimenting with electricity.
Okay.
And noticed something strange.
Uh-oh.
Whenever electric current flowed through a wire,
Yeah.
a nearby compass needle would deflect.
So that's when the connection between electricity and magnetism was discovered.
Precisely. Ørsted's observation revealed a fundamental truth.
Okay.
Electric currents create magnetic fields.
Huh.
Think about it. Every time you use a device that runs on electricity, you're harnessing the power of magnetism. This discovery sparked a wave of innovation,
Cool.
leading to the invention of the electromagnet.
And an electromagnet is basically a coil of wire wrapped around a magnetic core, right?
That's it.
Okay.
By running an electric current through the coil, you create a much stronger magnetic field than a permanent magnet alone.
Right.
This simple but powerful invention paved the way for a technological revolution.
The notes list a ton of inventions that stemmed from this discovery.
Yes.
The telegraph, electric motors, generators.
And don't forget the telephone. Alexander Graham Bell's invention wouldn't have been possible without understanding the interplay between electricity and magnetism.
Oh, that's right, yeah.
And then, of course, there's Nikola Tesla.
Oh, yeah.
His groundbreaking work with AC motors and generators
Yeah.
revolutionized the way we generate and use electricity.
Wow, it's amazing how one fundamental discovery can have such a profound impact.
It really can.
But let's dive a little deeper into the science. How do we actually visualize these magnetic fields created by electric currents?
That's where the right-hand rule comes in. It's a handy tool for visualizing the direction of the magnetic field around a current-carrying wire.
A right-hand rule. Okay.
Imagine you're holding the wire in your right hand with your thumb pointing in the direction of the current.
Okay, I'm picturing it, so then what?
Now curl your fingers around the wire. The direction your fingers curl represents the direction of the magnetic field.
So if I reverse the direction of the current, the magnetic field also reverses direction.
Exactly.
Okay.
Remember Ørsted's compass experiment?
Yeah?
The compass needle deflected in one direction when the current flowed one way, and in the opposite direction when the current was reversed.
Right.
The right-hand rule helps you predict that deflection.
That's super helpful. Our notes also mention a physicist named Ampere,
Yeah.
who made some important contributions to this field.
Yes, André-Marie Ampère.
Okay.
A brilliant mind. He developed mathematical formulas to calculate the strength and direction of magnetic fields.
Nice.
His work was crucial for understanding how magnetic forces behave. One of his key formulas calculates the magnetic field around a loop of wire carrying a current.
Okay.
The larger the current, the stronger the magnetic field.
That makes me wonder, how do we create those super strong magnetic fields used in MRI machines?
That's a great question. MRI machines use something called a solenoid.
Solenoid.
Basically a coil of wire with many loops stacked together. By passing a large current through this solenoid, we can create an incredibly strong magnetic field.
So it's like a supercharged electromagnet.
Exactly. And here's a mind-blowing fact.
Okay.
Those massive solenoids used in MRI machines are actually superconducting magnets.
Superconduct.
Meaning they have zero electrical resistance.
Oh, wow.
This allows them to carry enormous currents without heating up and generate those powerful magnetic fields needed for medical imaging. It's pretty amazing to think that we're using magnetism to see inside the human body.
It really is. Okay, we've talked about electric currents creating magnetic fields.
Yeah.
But what about magnets themselves?
Right.
What makes them tick? The notes mention these things called magnetic dipoles.
Think of it this way. Every magnet, no matter how big or small, has a north pole and a south pole. Those poles act like tiny little magnets within the larger magnet.
Right.
We call these tiny magnets magnetic dipoles.
And these dipoles are created by currents flowing in circles like an electron orbiting an atom's nucleus.
That's one way they can be created. Even a spinning proton creates its own magnetic dipole. Now, here's an interesting comparison.
Okay.
We also have electric dipoles. Formed by separated positive and negative charges.
Yeah.
But here's the catch. Electric dipoles neatly align themselves in a uniform electric field.
Yeah.
But magnetic dipoles are a bit more finicky.
Why is that? Are they like those fridge magnets that never seem to stay put where I want them?
That's a great analogy. It's because creating a perfectly uniform magnetic field is much harder than creating a uniform electric field.
Okay.
Those tiny magnetic dipoles are constantly trying to find their most comfortable spot in the magnetic landscape.
So how do they behave in a magnetic field?
They're always trying to minimize their energy. They do this by aligning themselves with the field lines and moving towards areas where the field is strongest. It's like they're constantly seeking the path of least resistance in the magnetic field.
That makes sense.
Yeah.
But our notes also mention different types of magnetic materials found in nature. It's not just lodestones, right?
Absolutely. We have paramagnetic materials, which are weakly attracted to magnets and slightly increase the strength of the magnetic field around them. Then there are diamagnetic materials, which are actually weakly repelled by magnets and slightly decrease the strength of the field.
So both of those have fairly subtle effects on magnetic fields.
Yes.
But then we have the real heavy hitters.
The superstar.
Ferromagnetic materials.
Yes, ferromagnetic materials are strongly attracted to magnets and can dramatically amplify the magnetic field.
Wow.
We're talking up to 1,000 times stronger. These are the materials we use to make powerful electromagnets and those permanent magnets we use every day. Think iron, nickel, and cobalt. They're all ferromagnetic.
Wow. That's a huge difference.
Yeah.
What makes them so powerful?
It all comes down to their atomic structure.
Okay.
Let's zoom into the microscopic level. Ferromagnetic atoms have unpaired electrons in their outermost shells.
Wow.
These unpaired electrons create tiny atomic magnets.
So each atom in a ferromagnetic material is like its own little magnet.
Exactly. And here's where things get really interesting.
Okay.
Quantum mechanics plays a crucial role. These tiny atomic magnets don't just point randomly in any direction.
Right.
They actually interact with their neighbors and try to align their magnetic fields, forming regions called domains.
Domain?
Within each domain, all the atomic magnets point in the same direction, creating a stronger overall magnetic field.
So a ferromagnetic material is basically a bunch of tiny magnetic domains all pointing in different directions.
Right. Initially, they're random.
Okay.
But when you apply an external magnetic field, something fascinating happens. The domains that happen to be aligned with the external field start to grow while the others shrink. It's like a magnetic tug of war.
This is reminding me of those diagrams in our notes, the hysteresis curves.
Yes. The hysteresis curve is a visual representation of how a ferromagnetic material magnetizes and demagnetizes. It shows the relationship between the applied magnetic field and the material's overall magnetization.
And the shape of that curve tells us whether we're dealing with a soft or hard magnet, right?
You got it. Soft magnets are easy to magnetize and demagnetize.
Okay.
They have narrow hysteresis curves and low remanence.
Right.
Meaning they lose their magnetism easily when you remove the external field. This makes them perfect for electromagnets because we want them to turn on and off quickly.
And hard magnets are the opposite. They hold on to their magnetization and are tough to demagnetize.
Exactly. They have wide hysteresis curves and high remanence, making them ideal for permanent magnets. Think of the magnet on your refrigerator and data storage.
That makes sense. We've covered a lot of ground here, from naturally occurring magnets to the atomic structure of ferromagnetic materials. It's amazing how magnetism works at so many different scales.
It really is.
And we've only just scratched the surface.
That's right.
There's so much more to explore. Stay tuned, because in Part 2, we'll delve into the incredible world of MRI machines, unravel the mysteries of forces and magnetic fields, and discover how Faraday's law revolutionized our world. It's going to be electrifying.
For sure.
Welcome back to our deep dive into the fascinating world of magnetism.
We're ready for more.
In Part 1, we explored the history of magnets.
Yes.
Dove into the atomic structure of ferromagnetic materials, and learned how electric currents create magnetic fields. Now we're going to take that knowledge and see how it's applied in some incredible real-world technologies.
Absolutely. That's the fun part.
Yeah, it is.
Seeing how it all works.
So we left off talking about ferromagnets.
Yes.
And how their ability to amplify magnetic fields makes them so useful.
Exactly.
And you promised we'd uncover the secrets behind those amazing MRI machines.
Yes.
So I'm eager to hear more about that.
Okay.
I remember from class that MRIs use giant superconducting solenoids to generate powerful magnetic fields.
That's right. Remember how we talked about solenoids being like supercharged electromagnets?
Yes.
Well, in an MRI machine, it's like they're on steroids. We're talking magnetic fields hundreds of times stronger than the Earth's magnetic field.
That's incredible. And the superconducting wires are a key part of making that happen, right?
Yeah.
Because they have zero resistance, so they can carry huge amounts of current without heating up.
Exactly. That's how they can generate those incredibly powerful magnetic fields.
Right.
But here's something you might not know. MRI machines don't just use one giant magnet.
Oh.
They also have these things called gradient coils.
Gradient coils. I don't remember learning about those. What do they do?
They generate varying magnetic fields,
Okay.
which are crucial for creating those detailed images we see in MRI scans.
Oh, they're important.
It's like having a magnetic spotlight that can focus on different parts of the body.
That's fascinating. So the gradient coils are sort of like the unsung heroes of MRI, creating those precise variations in the magnetic field.
Yeah, I guess you could say that.
Okay. What about those interesting clanging and banging noises you hear during an MRI scan?
Oh, yeah.
I always thought it was the main magnet making all that racket.
Actually, that's the sound of the gradient coils rapidly switching on and off as they create those variations in the magnetic field.
Oh, I see.
Think of it as the MRI machine taking a series of snapshots from different angles.
Right.
And the gradient coils are responsible for adjusting the focus for each shot.
Wow, I had no idea. So it's really a carefully orchestrated symphony of magnetic fields working together to create those incredible images. Okay, shifting gears a bit.
Okay.
Our notes also talk about forces in magnetic fields. It says, charged particles experience a force when they move through a magnetic field.
That's a fundamental principle of electromagnetism.
Okay.
The magnitude of that force depends on a few factors. The strength of the magnetic field,
Okay.
the charge of the particle, and the velocity of the particle.
So a faster-moving particle with a greater charge would experience a stronger force.
Yeah.
That makes sense intuitively. Is there a way to visualize the direction of that force?
Absolutely. We can use our trusty right-hand rule again, but with a slight twist.
Okay.
Imagine a positively charged particle moving through a magnetic field.
Right.
Point your fingers in the direction of the particle's velocity, and then curl them toward the direction of the magnetic field.
And my thumb points in the direction of the force acting on the particle.
You got it. Now, here's an important point. A uniform magnetic field, meaning one with the same strength and direction throughout, will only change the direction of a charged particle's motion. It won't affect its speed.
Wait, why is that? If a force is acting on the particle, shouldn't it speed up or slow down?
That's a great question. It has to do with the nature of the magnetic force. It's always perpendicular to the particle's velocity. And in physics, work is only done when a force acts in the same direction as the displacement. Since the magnetic force is always perpendicular to the velocity, it does no work on the particle.
So the particle's kinetic energy stays constant?
Right.
It just keeps changing direction.
Yeah.
That's pretty mind-blowing.
It is pretty cool.
It's like it's on a magnetic roller coaster.
It's a great analogy.
Okay.
And this principle is what makes a device called a mass spectrometer possible.
A mass spectrometer. Okay.
It's an ingenious invention that uses magnetic fields to separate ions based on their mass-to-charge ratio.
So you're telling me we can use magnetic fields to identify different isotopes of an element and even measure their masses.
Exactly.
Hmm.
Mass spectrometers have been invaluable tools in various scientific fields for over a century, from chemistry and physics to archaeology and forensics.
Wow, that's amazing.
Yeah.
Okay, so we've talked about individual charged particles.
Yeah.
But what about current-carrying wires?
Right.
Do they experience forces in magnetic fields as well?
Uh-huh.
After all, a wire carrying current is essentially a stream of moving charges, right?
You're absolutely right.
Okay.
Just like individual charged particles, a current-carrying wire will experience a force when it's placed in a magnetic field.
Right.
And guess what? We can use the right-hand rule again to figure out the direction of that force.
Okay, I'm intrigued. How does it work this time?
It's very similar to the rule for individual charges. Point your fingers in the direction of the current flowing through the wire, and then curl them toward the direction of the magnetic field. Your thumb will point in the direction of the force acting on the wire.
Got it. So if we have two parallel wires carrying current, they would actually exert forces on each other, right?
Precisely.
Yeah.
If the currents flow in the same direction, the wires attract each other. If the currents flow in opposite directions, they repel. And here's a fun fact. This force between parallel wires is actually what led to the definition of the ampere, the unit of electric current.
Wow. I never knew that.
Yeah.
So this seemingly simple interaction between wires underpins our entire understanding of electricity.
Yeah,
That's pretty amazing.
it is.
And it's also the fundamental principle behind electric motors.
Exactly.
We can use magnetic fields to make coils of wire rotate,
Yeah.
converting electrical energy into mechanical energy. Think of all the things powered by electric motors, from simple fans and blenders to complex machines and electric vehicles.
It's pretty incredible.
So a spinning electric motor is essentially a carefully choreographed dance of magnetic forces.
That's a fantastic way to put it. It's a beautiful example of how understanding fundamental physics can lead to incredible technologies that shape our world.
Absolutely. Speaking of world-changing discoveries,
Yes.
our notes mention Faraday's law is another pivotal moment in the history of electromagnetism.
Absolutely.
Sounds like this one is a biggie.
It is.
Michael Faraday's discovery was truly revolutionary. He found that a changing magnetic field can induce an electric current in a nearby conductor.
Exactly.
So if I move a magnet near a loop of wire,
Yeah.
I can actually create a current in the wire just by changing the magnetic field.
Yeah.
That's wild.
It is pretty amazing.
And the faster you move the magnet, the greater the induced current.
That's right.
This principle is the foundation for electric generators
Yeah.
and transformers, the technologies that power our modern world.
That's right.
Hold on, generators? Transformers?
Yeah.
We're talking about the backbone of our entire electrical grid, right?
Huzzah!
Faraday's law makes it possible to generate electricity on a massive scale and transmit it efficiently over long distances. It's hard to overstate the importance of this discovery. Every time you turn on a light or charge your phone, you're benefiting from Faraday's brilliant insight.
Absolutely.
Wow, my mind is officially blown.
It is pretty remarkable.
So how does this induced current actually work? What's happening at the atomic level?
Think about the electrons in the wire.
Okay.
When a changing magnetic field passes through the wire,
Yeah.
it creates an electric field.
Okay.
This electric field pushes the electrons, causing them to flow, and that's your induced current.
And the direction of the current depends on the direction of the changing magnetic field.
Exactly. There's a principle called Lenz's law that states the induced current will always oppose the change in magnetic flux that caused it. It's like the wire is trying to resist the change.
So if the magnetic field is increasing, the induced current will flow in a direction that creates a magnetic field opposing that increase.
You've got it.
Okay.
It's all about maintaining a kind of magnetic equilibrium.
Okay.
And this principle has some interesting consequences.
Like what? Give me some real-world examples.
Well, think about car engines.
Yeah.
They use something called an ignition coil,
Right.
which is essentially a transformer.
Okay.
When the magnetic field in the coil rapidly collapses, it induces a high-voltage spark, igniting the fuel and making your car go.
Wow. So Faraday's law is responsible for getting our cars going.
Yeah.
That's incredible.
It is pretty cool.
What other cool applications are there?
Here's another one. Regenerative braking.
Okay.
You know how some hybrid and electric cars can recharge their batteries while braking?
Yeah.
That's Faraday's law in action.
How does that work? I've always wondered about that.
As the car slows down, the wheels spin magnets past coils of wire. This changing magnetic field, induces a current,
Okay.
which flows into the battery and charges it up.
So it's like they're using the braking energy.
It's a clever way to recapture some of the car's kinetic energy that would otherwise be lost as heat.
So we're essentially turning motion into electricity?
Precisely.
That's so cool.
And it gets even cooler.
Okay.
Have you ever wondered how an electric guitar works?
Oh, yeah?
Those pickups that capture the sound of the strings, they rely on Faraday's law, too.
No way. How so?
Each pickup has a magnet and a coil of wire.
Okay.
When you pluck a string,
Yeah.
it vibrates near the magnet, disturbing the magnetic field.
Okay.
This induces a tiny current in the coil,
Right.
which it's amplified and sent to the speakers,
Right.
creating that signature electric guitar sound.
So every guitar riff, every soaring solo,
Or every power chord.
it's all thanks to Faraday's law. That's mind-blowing. It's amazing how this one principle has so many diverse applications.
It truly is a fundamental principle with far-reaching consequences.
Okay, our notes also mention this concept called inductance, which is playfully called the dark side of Faraday's law. That sounds a bit ominous.
Oh.
What is inductance all about?
Well, it's not really a dark side so much as another interesting consequence of Faraday's law.
Okay.
Inductance is essentially the tendency of a conductor to oppose changes in current flowing through it. It's a bit like inertia for electricity.
So if I try to increase the current flowing through a conductor,
Yeah.
inductance pushes back,
Right.
trying to keep the current at its previous level.
Exactly.
Oh, okay.
And it does this by inducing a voltage that opposes the change in current.
Oh,
It's all about maintaining a kind of electrical status quo.
so inductors are kind of like resistors,
Yeah.
but instead of resisting the flow of current, they resist changes in current.
That's a good way to think about it. And just like resistors have a specific resistance, inductors have a property called inductance, measured in henries. The higher the inductance, the stronger the opposition to changes in current.
So what determines the inductance of a conductor?
It depends on several factors.
Okay.
The material the conductor is made of, its shape, and if it's a coil, the number of turns of wire.
Okay.
We have a formula for calculating the inductance of a solenoid, remember? That's
Right.
basically a coil of wire.
Right.
The inductance is proportional to the square of the number of turns,
Yeah.
the area of the coil,
Uh-huh.
and the permeability of the material inside the coil.
So more turns, a bigger area, and a higher permeability all lead to higher inductance.
Exactly. And that means a stronger opposition to changes in current.
Okay.
Now, here's a cool connection. Inductors can actually store energy in their magnetic fields. Remember those massive solenoids and MRI machines?
Yes.
They're essentially giant inductors storing huge amounts of energy.
Wow. It's amazing to think about all this energy locked up in magnetic fields just waiting to be harnessed. It makes you wonder about the possibilities. Okay, so we've covered a lot of ground here. Forces, generators, inductance. What an incredible journey. Where do we go from here?
Well, in part 3 of our deep dive, we'll trace the fascinating journey of electricity from power plants all the way to your home.
Ooh.
We'll unravel the mysteries of transformers, explore the difference between 120-volt and 240-volt outlets, and even demystify that somewhat cryptic concept of RMS voltage.
Sounds electrifying.
Oh.
Stay tuned, folks. We'll be back in a flash with the final part of our magnetic adventure. Welcome back to the final part of our deep dive into the captivating world of magnetism. It's been quite a journey. It really has. We've covered a lot of ground from the basic principles of magnets and magnetic fields to their mind-blowing applications in MRI machines,
Absolutely.
electric motors,
Right.
even electric guitars.
Yeah, it's amazing how it all comes together.
Now get ready for an electrifying journey. As we trace the path of electricity from those giant power plants all the way to the outlets in your home.
All right, let's do it.
From power plants to our homes, it's a fascinating story.
It is, and as we'll see, magnetism plays a crucial role every step of the way.
Okay.
It all starts at the power plant,
Okay.
where generators harness the power of Faraday's law to produce electricity on a massive scale.
Right, Faraday's law.
Yeah.
The idea that a changing magnetic field can induce an electric current in a nearby conductor.
Exactly.
So at power plants, they're essentially spinning coils of wire within magnetic fields to create that flow of electrons, right?
That's exactly it. And they use a clever system called three-phase power,
Okay.
which is more efficient for transmitting large amounts of power over long distances.
Mm.
That's why you see those high-voltage power lines coming in groups of 3.
Three-phase power. That sounds pretty complex.
It is a bit more involved than just a single AC current, yeah.
Can you break it down for me?
Sure. First, let's quickly recap the difference between AC and DC current. Okay.
DC current flows in one direction, like the current from a battery.
Right.
AC current, on the other hand, constantly reverses direction.
Yeah, it flows back and forth.
Exactly, like a wave.
Right.
Now with three-phase power, we have three separate AC currents flowing through those three power lines.
Okay.
Each current varies like a sine wave, but they're offset from each other by 120 degrees.
So it's like having three separate waves, but they're all perfectly timed so they work together.
Precisely.
Eh.
It's a very elegant and efficient system for transmitting power.
That's pretty neat. But why do they need to boost the voltage so high? Those transmission lines carry thousands of volts, right?
They do.
That seems dangerous.
It is dangerous, which is why those transmission lines are kept so high in the air.
Right, well away from people and objects.
Exactly.
Okay, so it is dangerous, but there's a good reason for it.
Yeah, the reason for those high voltages is to minimize energy loss during transmission.
I see.
You see, higher voltage means lower current for the same amount of power.
And lower current means less energy is lost as heat in the wires.
That makes sense. It's like trying to send a package through a narrow pipe versus a wider one.
Yeah.
The wider pipe offers less resistance,
Right.
allowing the package to flow through more easily.
That's a great analogy. Now, as the electricity gets closer to your neighborhood,
Okay.
it goes through substations where transformers step down the voltage to safer levels for distribution.
Like a step-down process from
Yeah.
thousands of volts down to something our homes can handle.
Precisely.
But how does that final step work? How does the electricity actually get from the power lines into our houses?
That's where those split-phase transformers come in.
Split case, okay.
You often see them mounted on utility poles.
Right, I've seen those.
They take the high voltage from the power lines and split it into two lower voltages, typically around 170 volts each.
Okay, I'm following so far.
All right.
So each side of the transformer provides 170 volts.
Yeah,
But wait, our wall outlets are 120 volts, right?
right.
Where does that 120 volts come from?
That's a great question. It's all about how the electricity is wired within your house.
Okay.
The two sides of the transformer are actually 180 degrees out of phase with each other.
Out of phase. Okay.
That means the voltage on one side is peaking,
Yeah.
while the voltage on the other side is at its lowest point, and vice versa.
So the two sides are like mirror images of each other, with their voltages doing opposite things.
Exactly. And this phase difference is key.
All right.
Half of your house's circuits are connected to one side of the transformer,
Okay.
while the other half are connected to the other side.
I see.
So each individual circuit only receives 170 volts.
Ah, I see. But we still haven't explained that 120 volt number.
Right. The 120 volts we typically refer to is actually the root mean square RMS voltage.
RMS voltage.
It's a way of representing the effective voltage of an alternating current.
Okay.
To understand it, imagine you're graphing the voltage of an AC current over time.
Right.
It's constantly fluctuating, going up and down like a wave.
Right.
The RMS voltage is a kind of average value of that fluctuating voltage.
I see. So instead of using the peak voltage,
Yeah.
which is the highest point on that wave, we use this RMS voltage,
Right.
which gives us a more representative value of the actual voltage our appliances experience.
Exactly. For a standard sine wave, like the AC power we use, the RMS voltage is about 70.7% of the peak voltage.
Okay.
So even though the peak voltage coming from one side of the transformer is 170 volts, the RMS voltage that we actually use is closer to 120 volts.
Okay, that clears things up.
Yeah.
So we've got the electricity entering our homes at around 120 volts RMS.
Right.
But what about those 240 volt outlets we use for bigger appliances?
Oh, yeah.
Like electric stoves and dryers.
Those appliances need more power.
Okay.
And they get it by tapping into both sides of the split-phase transformer.
Oh, I see.
Instead of connecting to just one side,
Yeah.
they connect across both sides, giving them the full 240 volts.
So it's like accessing the full potential of the transformer.
Precisely. And that higher voltage is necessary to deliver the increased current those powerful appliances demand.
This is all starting to click now.
Good.
From those massive spinning generators at the power plant
Uh-huh.
to the familiar outlets in our homes, it's incredible how magnetism is at the heart of our entire electrical system.
It truly is a testament to the power of fundamental physics and human ingenuity.
And it all goes back to those ancient lodestones and our enduring fascination with this fundamental force of nature.
Absolutely. It's been a fascinating journey through the world of magnetism, hasn't it?
It really has. We've come a long way on our magnetic journey, exploring the history, the science, and the amazing applications of magnetism. I have a feeling you're going to ace that Physics 220 exam.
I think so too. And remember, this is just the beginning.
Right.
The world of magnetism is full of exciting possibilities waiting to be discovered.
Yeah.
So keep exploring, keep questioning, and who knows what incredible magnetic technologies the future holds.
Absolutely. The possibilities are endless.
They are.
Thanks for joining us on this electrifying adventure through the world of magnetism. Until next time.